Disclaimer. The views expressed in this video reflect the opinions of the creator and may not align with widely accepted beliefs. Viewers are encouraged to consider multiple perspectives and conduct their own research before forming conclusions.
Hello. Welcome to another video. In episode 11, I mentioned that in our timeline, light bulb research led to the discovery of the Edison effect. That discovery, in turn, enabled the development of vacuum tube technologies, which eventually led to the creation of klystrons. In parallel with klystrons, and also as a result of our advancements in vacuum tube technology, we developed another device called a magnetron. I believe the ancient Egyptians followed the same path that we would later take. I think they too developed magnetrons in parallel to klystrons. In our timeline, in 1940, John Randall and Harry Boot developed a prototype cavity magnetron, a groundbreaking device for generating microwaves at the University of Birmingham. However, the United Kingdom lacked the financial and industrial capacity for large-scale production. In an act of cooperation, Winston Churchill offered the magnetron, smaller and more powerful than any existing design, to the United States in exchange for financial and manufacturing support. The American historian James Finney Baxter III described it as the most valuable cargo ever brought to our shores. By early 1941, mass production had enabled portable airborne microwave radar systems to be fitted onto American and British aircraft. These systems, vastly superior to their German counterparts, gave the Allies a significant advantage, directly shaping the outcome of World War II. One of the most significant British innovations of the war, the cavity magnetron, is now used worldwide in microwave ovens. A magnetron is a cavity resonator that uses cavities to generate microwaves. Its frequency and efficiency depend on precise manufacturing, as even small imperfections can disrupt resonance. Magnetrons can interact with external cavities without a direct physical connection. These external cavities can couple electromagnetically to the magnetron's internal cavity resonators through waveguides or radiative coupling. This allows energy transfer and resonance without direct electrical contact. This concept is sometimes used in advanced microwave engineering to modify frequency characteristics or enhance performance. Also in episode 11, I spoke about how in the artwork, JED pillars seem to have been replaced by vase-like objects and horn antennas. This process repeated as these also lost their prominent place in the artwork to what I suspect are caricatures of early magnetrons. Their art appears to have evolved from this to this, and then to this. Here's what an early magnetron looked like. The pipe around the outside forms a water cooling system. Now here's what appears to have replaced the vases in the artwork. You'll notice the spiral-shaped appendage, which I believe represents the cooling system. Also, note that with the vase-like objects, there was typically one lotus antenna per unit. In contrast, these caricatures of vintage magnetrons sometimes feature up to 5 lotus antennas per unit. Magnetrons come in quite a few variations, and I believe that's reflected in the artwork. This mural is known as the Osiris Stargate device. I don't yet have an interpretation for the mural as a whole, but take a look at the bottom left corner. These devices appear to be illustrations of more modern-looking magnetrons, something along the lines of these. Here's a similar mural. It's known as the Osiris device. These are not the official names. They were given by investigative mythologist William Henry. The murals can be found on the walls of the Osiris Chapel at Abydos. The tall object in the center with the blue top resembles a variation of the Jed coils. However, instead of 3 coils, it has 4 blue bands. I suspect this represents what we refer to as a sapphire-loaded cavity oscillator. A sapphire-loaded cavity oscillator is a device that generates extremely stable and precise frequencies. It utilizes a sapphire resonator to produce signals with minimal noise or fluctuation, making it ideal for applications requiring high accuracy. Think of it like a super steady clock. It keeps time at a precise frequency, which is useful in things like high-performance radar systems, terrestrial communications for stable signal transmission, deep space communication, and quantum research. It's one of the best tools for keeping signals sharp and reliable. Sapphire-loaded cavity oscillators are most commonly found operating in the 8 to 18 GHz range. Next, in the bottom left of the mural, there are 3 vase-like objects and a larger vessel. I suspect the vase-like objects are meant to represent klystron-type amplifiers, perhaps something similar to these. And I believe the larger vessel to the right of them is meant to represent a cavity resonator. Here's one of those. I suspect the circular object above the resonator represents a component called a circulator. Here's what those look like. And as I've mentioned in previous videos, I think the spouts represent waveguides. Now, if we look in the bottom right corner, there are 5 magnetrons with horn antennas. Here's an example of what modern variants look like. A recap of the components. A sapphire-loaded cavity oscillator. Three klystron amplifiers. A resonant cavity. A circulator. A waveguide. Five magnetrons. And 5 horn antennas. Together, these components could form the core of a powerful microwave transmission system, potentially for advanced radar applications, deep space communication, or terrestrial communication. Here's how they would function together as a transmitter. Step 1. The sapphire oscillator. Generates a stable and precise microwave signal, serving as the foundation for the system. Step 2. The 3 klystrons. Amplify the oscillator's signal, boosting its power level for further processing. Step 3. The circulator. Directs energy efficiently, preventing interference and ensuring smooth transmission flow. Step 4. The resonant cavity refines and enhances specific frequencies, ensuring signal purity. Step 5. The waveguide. Channels the processed microwave energy efficiently towards the final amplification stage. Step 6. The magnetrons generate additional high-power microwave energy, further strengthening the signal for transmission. Step 7. Finally, the horn antennas convert the amplified signal into free space radiation, broadcasting it in the desired direction. The sapphire-loaded cavity oscillators mentioned in this episode typically operate at frequencies between 8 GHz and 18 GHz, although custom-made solutions are available for frequencies outside this range. The overall microwave frequency spectrum extends from 300 MHz to 300 GHz, meaning the typical operating range of these oscillators covers only a small segment of the total microwave spectrum. I've mentioned these items a few times already. They were discovered among King Tut's treasures. While they are commonly referred to as trumpets, I previously suggested that they might have been used as waveguide and horn antenna combinations. We also examined the lotus flower designs that adorned them. The shape and materials of these objects make them suitable for use as waveguide and horn antenna combinations. However, it is their dimensions that determine the frequency at which they can operate. The precise dimensions of these trumpet-like structures make them well suited for functioning as both waveguides and horn antennas, with an optimal operating frequency range of 13 to 20 GHz. To recap, the typical working range for the sapphire-loaded cavity oscillator is between 8 and 18 GHz. And the optimal frequency for these specific waveguide and horn antenna combinations is 13 to 20 GHz. The conclusion is that these components would work well together. And that brings us to the end of the video. Thank you to those who are still watching, and goodbye.